Hello everyone, my name is Pratik and this is another video on OpenFoam. So today I will be showing you how you can model flow in contracting pipe. So basically the pipe which is like has a more radius here and it is contracting, and how the pressure drop and velocity changes along the whole path that we will be modeling today. And in the end you can expect these kind of results. So this shows the pressure profile in the pipe, and here this shows the velocity profile. So yeah, so now we'll go forward with the modeling, and the software that we will be using is to mesh the whole body would be open source software called Salome. So if you just go on Google and type Salome mesh. So this is the software here. If you click here, so this is a software. Best thing is that this is the open source software, so we will build our mesh on this software. So you can download this software. uh, if you type it here and click here, you can download. There are different versions of it are there. So I am using Windows software, so for Windows you can just click on here and download it. So I have that this software already downloaded in my PC, so I will just use that one. So what we will do is we will create mesh on Salome and then import it in OpenFoam and perform our simulation. And then we will do the post processing with ParaView, which is another open source software. So I have my pipe geometry here in my Fusion 360. I will just save it. I will just export it in the step format. I will just name it contracting pipe and save it in .step format. Export. So we have exported our file, our geometry. Now we will open the software which we will use to create the mesh. So this is the software version which I will use. Click open. So now the Salome software is open. So first we will click on this option and click on geometry. So there is one shaper as well. So shaper is like you can build your own geometry on the Salome software. But we since we already have our geometry built in Fusion, so what we will do is we will just import our geometry in the Salome software. So we will just click on geometry and then file, and you will see the import option here. So we have our file already saved in step format, so we will just click on step, and here you see just save our pipe. So click on contracting pipe, not step, and open. So click on 3D stereo projection, and you will see here. So now our geometry is imported into Salome. Now our geometry is imported. What we will do is we will create phase groups. So to create phase group, as in we want to assign which is our inlet condition, which is our outlet condition, which is our wall for this geometry. So we will, for that what we will do is we will click on new entity and group and create group. So once you create group, so firstly we will choose inlet. So inlet is our this surface. So since it's a surface, so we'll click on shape type is surface. We'll click here on shape type and name it at inlet. So inlet, and for selecting, just click on this and add. So this surface is selected. So this is our inlet, and apply and close. So you see here. So our inlet is selected. It will come here as well. So now similarly we have to choose outlet and wall conditions as well. So we will click on new entity, group, create group, body 2. So now we will choose our outlet condition. Click on outlet, rotate it, and so this is our outlet. So just click on this surface and add. So now we have added our outlet as well. Apply. So next is to choose our wall. So wall is like we have to select all the boundaries except the inlet and outlet. So what we will do is we'll just name it wall and click on select all option. So the select all selects all the boundaries. But what we have to do is we have to remove those boundaries which are inlet and outlet. So we'll just see which one is inlet. So this is 17, it's not inlet. 10, so you see 10 is the outlet, so we'll just click on remove. And now the third, I guess this 3, click on 3. It's now 17 and 22. So yeah, we'll remove 22 because it's our inlet condition. Remove. So now we have our wall. So apply and close. You can double check it by clicking here. This is you see. So I guess our wall is correctly defined. So we have defined our face groups. So next is we have to create the mesh. So now go on this again and there is a mesh option. Just click on the mesh. So new window will pop up and it can take some time. So now again we have to click on Windows 3D since scroll in. Yeah, you see our body is here. Now we have to mesh it. So to create new mesh, you have to click on create mesh option. Create mesh. Mesh type we will keep any. There are different options like triangular, quadrilateral, tetrahedral, hexahedral. We will choose any. So since our geometry is in 3D, so we have to provide the algorithm for 3D. For that we will choose NetGen 3D. So why we are choosing NetGen 3D and what all different options are there, what all we can use, we will not cover that in this video. For that I will create a separate video. So here you have to choose the algorithm and then here in the hypothesis you just click on this settings option. Here you can give the parameters for the maximum and minimum element size. So just click on NetGen 3D. Currently it's like maximum size is 0.0008 and minimum size is 0.0001. So in meters, because our geometry is in meter, click OK. So we will, for the timing, we will keep it as it is. And then for 2D, because for the surface 2D elements you have to define. So for 2D, what we will do is we will click NetGen 1D and 2D. Again, we have to click for the parameters. Again, we will keep them same for the time being, just to see what kind of mesh is generated. Click on OK and apply and close. And now click on this, right click on the mesh and click compute. So you see here 936 faces are generated with volume elements are like around from 1583, and this is our mesh. You see, currently the mesh is bit coarse, coarse. So you can see this surface is not properly meshed. We want it to be bit finer, or else we won't get better results. We go to mesh again, click edit mesh. You have to do like you have to do hit and trial and error and check for the best mesh. So currently I'm just doing some trial and error to the maximum size of the elements 0.02. So I guess so we have further refined our mesh. So you can see now I guess the mesh is okay. Just look to the outlet as well. So yeah, it has also has uh, more than I guess 15 elements. So we will not make it more fine mesh because we want to just run it fast. So now we will use this mesh for our simulation on OpenFoam. So we'll close it. Now what we have to do is we have to generate mesh groups as well. Similarly, what we did for our body like inlet, outlet, and wall. Sorry, so wall we have to rename it wall. So similarly, what we did for that, we have to create the mesh groups as well. So for that, what we do is just right click and click on create groups from geometry. So these they select all these inlet, outlet, and wall, apply and close. So you will see here now we get our inlet, outlet, and wall. They are repeated, you just delete it. So we have our inlet, outlet, and wall as a group. Now what we do is we click on mesh and import this mesh, export this mesh for the OpenFoam. Click on the mesh. Don't forget to click on the mesh because sometimes if you don't click on the mesh, you will get some warning and you won't be able to export the mesh properly. Just click on the mesh and click on file, export, and UNV. So now we save it as contracting file and save. So we have successfully created our mesh. So now our meshing is done. So now we start building our model on OpenFoam. So since I'm using my Windows PC, so I'm using Mobaxter to build my model on OpenFoam, basically to access the OpenFoam. So I'll just click on Ubuntu, which is installed here. So basically WSL, this Mobaxter gives me option where I can see uh, this panel is also there, and then I have different files where in which folder I am there and what all files are present. So this is in the left. This gives all the information. So so start with OpenFOAM. Basically, firstly we have to start from somewhere. Basically, OpenFoams has different tutorial models which are already present in the model, and we can use one of the model as a starting point. So firstly, we will go and access of OpenFOAM tutorial and see what all models are present. So for that, we will go to type cd and dollar and type foam tutorials. Click, and this will take you to the folder where all the models which have been created previously, the tutorial models, are present. So let's say this is like moving mesh. This contains tutorial which are related to moving mesh. Some are for isothermal fluid, or for the multi-phase flow, or for the incompressible fluid. So for our case, we have a simple flow in the pipe, and in the pipe we are assuming it to be like the water is flowing in the pipe. So basically, it's a incompressible flow. So you can see there are different folders for incompressible. There is incompressible volume of fluid, and then there is incompressible fluid. So we'll click in this model and see there are different models which are which have been developed for the incompressible fluid, the tutorials. So we will choose the best one for our case. So you just scroll down and you see there is option of, you see, planar contraction. So we will use this as a starting point, and this is a tutorial model on like on the planar contraction, where like the flow is contracting like from the bigger pipe to the smaller pipe, and we will use this as a starting point. So firstly, what we will do is we will copy this tutorial in our main, in the main folder where we will build our model basically. So to copy it, what we will click on this planar contraction. So we have our file location. We'll copy it, Control C, and go back to our original directory, cd cd OpenFoam, and we copy it here. So sorry. So I have my file already copied, but I will just type the command which you use to copy the file. So it's cp r, and then you copy your whole path for the file, and then you click dot. If you click this, then your folder will be created in this folder for the planar contraction. So I will not do it here. I already have my planar contraction model. So now I will show you how it how the tutorial example looks like basically. So for that, what I have already run my model. So go here. This is the model I have already run. So what I will do is I will open it. I will open it on the ParaView just to see how it looks. I'll click on the ParaView. So this is how ParaView looks like, and we will click on File, Open, and click on Planar Contraction, tut.foam, and OK. Click on Apply. So you see here, this is the tutorial example which was there. So here this currently shows the pressure. If you see the velocity, if you see here, the velocity reached to around 0.8 to 0.28 meter per second. from somewhere around 0.05 meter per second. So there is an increase in the velocity. So I guess the same thing would be happening for our case as well. So I guess we can use this as a starting point for our case. So now I will go back to we'll start creating our own model. So since this is already there, so this is already there, we will create a new folder for the planar contraction. We'll go to OpenFoam again, and what we will do is we will rename it. We'll name it, let's say, 4. Okay, and we just copy one more copy the file, the new folder from the tutorial model. So C to copy, we do CP R and path. So I guess path to copy. Yeah. So this was our path basically. So just right click. And you will see. Oh, we copied in this different folder. We have to copy it in this folder. So go to CD OpenFoam and type it. Okay. Yeah. So you'll see now we have a new planar contraction folder. Click. So currently, so since it's not, we haven't run any simulation on this yet. So this just shows the file. So not the extra post processing files, just the file which is contains the initial value and all the model parameters and the yeah. So just to see here, 0 file contains the P, the pressure, and the velocity details. So you see, so this is the, see here, yeah. So this contains the velocity conditions. So here u inlet, we are giving it 0.03876. It will depend on how you are in which coordinates you want your flow in. So yeah, so what we will do is we will go back to our folder and import our mesh file here. So click here to upload. So we installed, we exported our file in uh, yeah, in this folder we have our unv file. Click on here and open. So yeah, now we have our mesh file here, and we'll go to system. So here we have different files. So this block mesh stick file contains the information of the of the geometry. So if you right click here, you will see the geometry that I've shown you earlier of the two rectangular converging the contracting pipe. So since we already have our mesh from the Salome, so we don't need this file. So what we will do is we will just delete this, and yeah, now. So now we have this in UNV format, but we have to change it in the format which is supported by the OpenFoam. So for that, what we will do is we will type IDS2, click tab to UNV dot form to form. So this is change in IDS2 in form, and wait, we have to go first. We have to go to our folder as well. Now here we have to type form and then write the file file name, contracting pipe. Okay, contracting pipe. So yeah, you see here, this has this has successfully run. So we have our inlet on with 177 patches, outlet with 23, and the wall with 5200 patches. So we have successfully imported our file in OpenFoam, and you will see in the zero folder, in the constant folder, you will see the new folder will be generated with polymesh, and this contains the detail of our mesh. So what we will do is, and here you see we gave our we have defined our inlet in the form of this inlet, outlet, and wall. So we have to be consistent in our velocity and pressure files, so that like we have to keep the names same. So we go to polymesh and boundary. Then in the boundary, you see there is inlet. So yeah, it is same as our case, wall, outlet. But here we have to change wall type from patch to save it, because and go back. So this is now physical properties. In the physical properties, so viscosity will keep the same. We are not taking into account any momentum transport as of now. We are mostly concerned about the velocity and pressure profile. In order to make any changes there, we'll go to, now we make changes to our initial conditions and boundary conditions. So those details are here in the zero folder. From zero, u. So what you can make changes through Notepad as well, but what the other thing you can do is you can also use this command prompt also to make changes to the file. Let's say you want to make changes to our u file from here. So what we'll do is we click on vi. So first go to that 0 0. Now vi u. So now this is opened here. So to make changes here, we have to go into the insert mode and click on insert. Now we are in insert mode. Now we can make changes. Let's say we make the velocity as 0.02 as the inlet. Also, so here now we have to make them consistent based on our input mesh file, how we defined our input uh, phase groups, input mesh phase group. So for the us, if the inlet was written like I was capital, so just make capital, outlet, and wall was capital W. Yeah. So click escape, and so now we'll save it. Type Q. This will save our file with the updated value. And similarly, we'll make changes to the pressure file. Click VI, P, insert mode, change inlet, outlet. Yeah. So rest is we have to make see the constant polymesh. We have already made changes. We want already make changes here as well. This is also same system, and here we go to control dict file, which contains the information about the solver which is used, what is the starting time, what is the end time, what is the time step that you are using for the model. We'll keep all things same and try to run our model. So we'll go, yeah, so we are in this folder now. What we will do is we'll type foam run just to see whether, let's see whether the file runs or not, or it gives some error. Yeah. So simulation has finished successfully. So we all have it ran for 0.23 seconds. So to visualize it on ParaView, we'll type touch. Let's name it pipe contract.foam. We'll create new file here. So we have pipe contract.foam, and we will use this file to do the post processing. File, go to ParaView, file, open pipe contract, and apply. So now you see we have our results. So this shows the pressure profile in the cylinder, and here you get the velocity, magnitude of the velocity. This shows in the y direction the surface value. Yeah, so we gave the initial velocity of around 0.2, and we uh, on the edge, as soon as it converges, we expect the velocity to go high. So you can see here the velocity has reached somewhere around 0.99 meter per second. So there is an increase in the y direction velocity. Yeah. Now we further see more visualization tools. So just to see half of the cylinder, what is happening in the half, we can use this clip option. Just click on the clip. So you want to see this in this direction. Yeah, shows pressure in half. To remove this, we go here, go down, just untick this. You don't want to see the plane. So this is the pressure in half. Similarly, velocity profile is like this. So if you further, like if you see here, it's not properly done because the mesh is not that fine. You have to further do some mesh refinement on the geometry to get better results. But we haven't done that in this video, but you guys can try that by your own self. So now let's see how to draw the streamline plot to see the flow, to visualize the flow in much better way for that. So go on filter and just search here uh, stream tracer. You see here stream tracer option. Click, and now this is the direction where the streams in which the stream will be there. So we have to make it in plane with the cylinder. So for the point one, we have to give XYZ coordinates for point one and two, point one and two. So point one is like for us is 0, comma 0. Similarly, for this is in y direction, so this would be like 0, comma or length 0.08. Yeah, it's all right. And then Z is also 0, comma 0. And click apply, and then yeah. So yeah, don't see lines. To visualize them, we have to make this clip less opaque, and seed type is okay. We want seed type with point cloud. We want more focus on this part basically, where there's change in velocity happening. So for that, we have to place this point cloud here in this region. Yeah, and then click apply. So there's, you see there's one single line, so we have to increase the number of points for that. Let's say number of points, make it 500. So now you see there are streamlines. You can further make them 1000. Yeah. So this is how the stream lines are there. Since it's a laminar flow, you see they are like straight, almost straight. Uh, we can also use one more option which is called tube. So just to show the line in the tube format. For that, you can search tube here. So, tube. You see, this will come in the form of tubes. These streamline traces will come in the form of tube. We have to reduce the radius for our tubes. Apply. So yeah, you see here. So these are, you can perform more post processing visualization properties to this geometry. I will not go into much detail in this video. There are separate videos are there on YouTube which shows how to visualize the result in more better way. So yeah, that's all. We come to the end of the tutorial, and yeah, so what I will do is I will add these files in the GitHub and also attach them here in the on the YouTube channel as well. And if you have any questions, you can just write to me or email me. uh, I will be more than happy to help. So in the next tutorial I will show you how you can model the turbulent flow, and if there is some constraint in between, how the flow will be directed around that. So yeah, that's all. Thank you.